All right, welcome to today's lecture on engineering analysis, CHE 306. And we're going to start with the topic iteration methods. And so, firstly, I like to explain or introduce you to what we call numerical analysis. And so, what's numerical analysis and what does it entail? So what are we trying to do in numerical analysis? As you know that in engineering or in sciences, what we try to do majorly is to solve problems. What we try to do is to solve problems. And in the process of trying to solve problems in sciences, in engineering, and so forth, all right, what we do is a physical situation, or let me say a physical phenomenon, is firstly converted to a mathematical model. That is, you look at it and say, okay, something is wrong in the physical, you convert it to a what? A mathematical model. Now, when you convert this physical phenomenon to a mathematical model, most of the times, to solve this mathematical model, it leads you to what we call mathematical problems. Okay, when you form the mathematical model, you now need to solve it, right? So it leads to mathematical problems, and most of the times, these mathematical problems are not easy to be solved. Like you can't solve them in a direct form or in an exact form. I will explain what I mean by direct or exact. It's just like when you have your quadratic equation. When you have a quadratic equation, you know that if you use by factorization or whatever, you can get your two values. You can get your x1, you can get your x2, and you're fine. Okay, that has a fixed pattern, and you can get an exact solution. Okay, so in this process, when you encounter the mathematical problem, there needs to be a way you have to solve it efficiently, right? Okay, there needs to be a way you have to solve it efficiently. So what are the ways we use in solving it? That's exactly what I'm talking about. What are the ways we use in solving it? So when you have such a problem, when you have such a problem, or when you have problems like that, most of the time we use numerical analysis to solve or to develop a particular pattern, or let's say a technique to solve the problem such that we are going to have a solution, or let's say an approximate solution, okay, to the mathematical model you had formed. I'm going to give an example. Just follow me through. Okay. Now, you see, a numerical method can follow a pattern, or let me say, it can follow, yes, a pattern. And this pattern is sometimes called an algorithm, all right? Pattern, like a flow. It follows a pattern, it follows a flow. So an algorithm is like a complete and you see something that it is unambiguous, and it is a set of procedures that would lead to the solution of that mathematical problems that you had formed. All right, an algorithm will lead to what? It's like a procedure that will lead to the solution of the mathematical model that, or mathematical equation, I mean to say, that you had formed. Are you following me now? Okay, let me give you an example. It's just like saying, in your car, let's say your car, the driver the driver sends an input to the car. So we have input here. The driver sends an input into the car. All right. An example of the input is sent through the steering, to the steering. It is to the brake, etc. Those are the input that the driver sends into the car. Okay. Now, this input is actually being processed and converted to mathematical model. So inside of this mathematical model is the processing. All right, you are processing what the driver inputs into the car. Then when you are done processing it, there is output. Now, what is the output from the driver? The output is going to be in terms of the acceleration, in terms of the speed, and so on and so forth. So you can see that when you when the driver, put something into the steering, or maybe turns it, or into the brake, it doesn't just happen like that. It undergoes several processes. All right. Of course, it's control system. this has to, there is a sensor, there is the actuator that is inside of the car. There is sensor, there's the actuator. So what happens is that all of these things happen in a process, in an orderly manner. All right. Then you get an output. You get an output. And this output is the result of the inputs, which are also different parameters. Do you get it now? So in numerical analysis, all I'm simply saying is that there was a problem. You formulated something from that problem. It became mathematical model. To solve the mathematical model, you could have an algorithm. An algorithm follows a pattern, a way of solving a problem, just for you to get the solution, or to get not necessarily sometimes an exact solution, but in the real sense, you want to get an outcome from the problem that came. So that's what numerical analysis is about. And there are different approaches to solving numerical analysis, all right? Problem. There are different approach to solving, the mathematical model problems. There are different approach. So what we're going to be doing now is that we're going to be seeing some of those approaches and looking at how we solve them. Okay. And we are going to be using MATLAB in this course because MATLAB also helps us to solve some of these things using programming language. Of course, programming language is an algorithm also. Okay. Now, let's take it on from there. Now, we have mathematical model. Let me give an example because I've mentioned mathematical model. Let's see an example of what a mathematical model is. Let's see an example of what mathematical model is. So let's take it to the right. So mathematical model. Don't mind my pen. I don't know what's going on. Oh, sorry. So let's try to see an example of a mathematical modeling problem. Let's try to see an example. Most of the time, usually in mathematical modeling, you are going to be the one to interpret the problem and, try to solve it out mathematically. Okay, so we have a question here. The question says, the question is being displayed on the board right now. Question is being displayed. Okay. So the question says, a sphere of radius r, a sphere of radius r and density rho, a sphere of radius r and density rho is floating in water of unit density. Is floating in water of unit density. It is required to determine the depth h of the sphere that is below the water line. Show that the volume of water displaced is 1/3 pi h squared into bracket 3r minus h. Okay, so from your fluid mechanics 1, you know what buoyancy, you did buoyancy, and you know what buoyancy means. You know when the body is said to be floating. Okay, so when does the body float? What happens when the body floats? What is the principle that guides a body that is floating? Remember, it is sphere we are talking about here. You know that in buoyancy, it is possible that you have a body floating. You have something like this. You have a body that is balanced by the downward and upward force. Then you have a body that sinks to the bottom. Okay. So when the body floats, we're talking about this one here. Okay. Now, what is the principle that guides this body floating? Of course, you know it is what? From Archimedes' principle. And what does Archimedes' principle state? Archimedes' principle. All right. This you need to know yourself because we are formulating the problem. So they won't tell you anything. They expect you to know from all the knowledge of sciences you've learned from past. So you look at which of them can I apply to this problem to solve the problem. That's what it means. You're literally solving it from the scratch. Okay. Now, so Archimedes' principle is what governs when a body is floating. All right. So what's the principle? So Archimedes' principle states that when a body is floating in a fluid, all right, the weight of the fluid that is displaced the weight of the fluid that is displaced is equal to the portion of that fluid that is submerged or immersed in water. I'm just giving you a paraphrasing so you can easily understand. All right. Well, what I'm trying to say is that in this case, we are talking about a sphere, right? So the volume of the sphere that is submerged in water or that goes into the water is equal to the weight of the or equal to the weight or the volume of the water that is displaced from probably the container or something. Let me give an example. Just from this diagram I've drawn, we have, let's say we have a bowl here, and we have the water full to the brim. And so I drop a sphere inside of this water. So of course, it's going to look like this. So what we are trying to say is that this part or this portion of this sphere that is submerged is going to be equal to the water that will fall, that will be displaced out of this sphere. Do you understand that now? Okay, so let's draw the free body diagram of the sphere, and they are not asking us that the depth of the water that's the depth of the sphere rather that goes below the water is what we're trying to look for. That goes below the water, something like this. This depth, let's call it depth h. That's what we're trying to look for. Okay, so let's try to do the analysis. I'm going to draw the sphere out now so that you understand what I'm trying to say. Okay, so we have a sphere of this kind. Okay, now, of course, you know your sphere is in a 3D form. So let's give it the coordinates system. So I have along this direction, let's call this x. Along this direction, let's call this y. Along this direction, let's call this z. And of course, in your sphere, just like example is your earth, the middle, there is something we call the great circle, okay? Or let me call it, we call it the equator. And you know that your radius r is towards all direction in this sphere. Your capital letter R, that's the radius of the earth from the equator. It's the same in all direction. So let's put a hashing to this sphere. So the question is saying that the portion of this sphere that is submerged in water. So let's say this is the portion that goes into the water. Of course, this is floating. It will never go below. All right. This is not fluid mechanics. You should have done that in fluid mechanics. So now this is the sphere. I've defined my coordinates. Now let's go to the question, because you have to understand the question before we try to attempt it. Okay. Now, so let's go back to the question. So I'm going to read it again. Now, the question says, the radius is r, the density is rho, and it is floating in water of unit density. It is required to determine the depth h. As I've said, the h here, the depth h that goes inside of the water, this one here, below the water line. This is what we call the water line. This is the water line. Water line. Okay, so the depth h, the one that goes below, show that the volume of water displaced. Of course, this one that comes out like this, the volume displaced, we are told to show that it is equals to 1/3 by h squared, then 3r minus h. Okay, so this is the problem. How do we begin the problem? What are the basic knowledge you are expected to have known before you can attempt this problem? All right, you can see this middle of this sphere here. A very simple way to say this is the knowledge of your latitude and longitude. You see that this sphere, this equator is having a circle. And what is the equation of a circle you learned in your basic mathematics? You know, the equation governing a circle would be x squared plus y squared equals to r. All right, I know you are r squared. I mean, you are familiar with this x minus a squared plus x minus b squared equals to r squared. I hope I'm correct. It's not positive. It should be negative. Yeah, I believe. Okay, but of course, that's not our interest. That's not our interest for now. This is just what we need. All right. Now, since we've known that this is the equation that governs the circle, this is the equation that governs the circle. And you know, this part is a part that was immersed in water. So they call it H. H. The part that was immersed in the water, that's the height H. Height H. So don't forget this radius. I said it is the same. It is equal from the equator, from the great circles. All right. From the equator. So if R is constant, it definitely means that from this center to the bottom here is also R. And if that be the case, let me clean this and take it out. Let me make it better. So if that be the case, this place is going to be R minus H. That is, if from here, of course, this is a coordinate system. Let me extend it out. This is coordinate system. But from the top of this circle to the middle is R. From the top, from the middle here to the bottom is also R. So if the water, the part of the sphere submerged is H, so it's going to be R minus H. Is that okay? All right. Now, the next thing to do to solve this problem is this. Since you know that this is the part or this is the portion that is submerged, let me extend the coordinate system to this the circle below. So let me take it out. Let me take it out also. So if this direction, don't forget this direction is x, is x. So this place now towards this down circle, we can call it x prime. Okay, x prime towards this direction. This one down here is x prime. So if this one is x, this is x prime. All right, just pay attention to what I'm trying to do. Now, before I go into solving, let me take you back to something in longitude and latitude, because I'm going to be using the formula very soon. You remember that the we have small circles. Let's say we have small circles like this. We have small circles like this. Okay. So I told you that from the equator to anywhere along the sphere, R is constant. Is that correct? Yes, I did that. So it means from here, let me do it down for easy understanding. So let's say, so that it's not rough, because I've already taken this curve here. So if I say from the equator to this place is R, is that correct? Yes, R, that's radius of the earth. Okay, if that is R, from the center here, that is the center of this portion that is submerged below, to the body of this sphere is small letter r. We call them small circles, small letter r. And don't forget, I have defined this vertical as my y coordinate. I have defined the vertical as my y coordinate. So I can say that from the equator to this portion here, let me say it is y. Do you understand? This place is small letter r. That's the radius of the small circle. This is capital letter R. That's the radius of the head. All right. And then this vertical here to the portion of the small circle is y. You get the reason I'm doing that now. Okay. And you know that this place is called phi. It's called phi. It's called phi. Then now let's go ahead with our analysis. If this place is small letter r, don't forget, it is also same thing as, I can also say it is same thing as x. So why is it x? Look at the coordinate system I've defined. I've defined that towards this right-hand side is x. Even though I'm using small letter r here because it is small circle, capital letter R here because it's from the great circle, the coordinate system is still x. So this x is still valid here. Does that make sense? Yes. Okay. So if I want to make this r the subject of formula, all right, if I want to make this r the subject of formula, of course, I'm going to use something like Pythagoras theorem here. Pythagoras theorem here, or I can just use this equation I have at the top here. But this case now, it is now letter x because of the coordinate system I have defined. So if I make s the subject of formula, it's going to be x minus, don't forget from this, let me bring it out from this. So I have X here, I have Y here, I have R here. Okay, so it's going to be S equals to R squared minus, okay, minus Y squared all square roots. I believe you understand that. Okay, so if that be the case, let's go to our analysis. You know that the volume that is displaced, let's call this portion here, this small portion here, let's call it dh, because the y rather, because that's the coordinate system we have, the y, the small portion that went below the water surface. All right, let's call it the y. So let's say something like this, because this floats in a small portion, that small portion, very small compared to the other part. Let's call it the y. That's the y. The y. Okay. Now, if I have change in volume, of course, it's a small volume. Of course. Okay, let me take it from the beginning so that you get that. If I have volume is area times length. But in this case now, what's the length we're talking about? It is a vertical length. Let me bring it out. Let me bring it out. So I want to bring this small portion out. So look at it here. Like this. Like this. So if I want to calculate the volume of this guy here, don't forget this is the y. So it's going to be the area of this circle. This is a circle. Don't forget. Area of this circle times the height. That's this height is the y. So area times y. But now, because it is small volume that is displaced, if I say the v is going to be a dy. Okay? If I say the v is going to be what? A dy. And don't forget that the radius of the water level at the point of the sphere is given as, that is the radius of the water level at the point of this sphere. This one here, I've derived it at the top. I got x equals to r squared minus y squared square root. Okay. Now, what is the area of a circle? The area of a circle is pi r squared dy, pi r squared dy. And if I substitute for my, of course, this r here, in this case, the radius of this circle is s because of the coordinate I've defined. You can see this r and s are the same. So it's going to be something as pi x squared dy. Okay, so if that be the case, what is my x? My x here is same thing as, pi into brackets r squared minus y squared dy. Okay, so if that be the case, I'm going to integrate to get the entire volume, right? We are talking about elemental volume, but I want to get the volume of the fluid displaced, not the elemental. So if I integrate my volume, if I integrate the v, that's on the left, from 0 to v, and I'm integrating it at the right. Now, what's going to be my lower limit? What's going to be my upper limit? Okay, look at this sphere. Look at this bigger sphere. V is the volume, the entire volume from the sphere. That's what we're talking about now. So my lower limit is going to be from the center of this circle. Don't forget lower limit, just like say, where is it starting from? From the center of this circle to that point where the sphere was immersed, the depth of the sphere. So that's going to be r minus h. Don't forget, the sphere is actually moving downward. It's moving downward, and that downward is a y coordinate. So the beginning is going to be between r minus h, that's the lower limit, r minus h to r. Just like saying something like this. From here to here is the total distance, which is r. Okay, so, and this is actually the part that was immersed. This is r minus h. So if I want to find the total volume now, it's going to be this place, which is like the origin, okay, to this place. That's the upper limit. That's like the total. That's upper limit. that is from 0 to the max, that's upper limit. Then from this your origin to this r minus h, that's like your lower limit, because h is the portion we are looking for. H is actually what we need. H is what we need. Okay, so I'm going to be integrating it over pi into bracket r squared minus y squared dy. Okay, don't forget we are doing the mathematical modeling. So what do we do next? We are going to integrate. All right. So when I integrate the left hand side, I'm going to have v. I don't want to take it off the screen so you can see what I'm doing. So when I integrate the left hand side, I'm going to have v being the volume. When I integrate the right hand side with respect to y, so I'm going to have, let me put this, pi is a constant, take it out, pi, open your brackets, then r squared. If I integrate y with this first guy here, r here, I'm going to have r squared y, okay, minus, if I integrate this other guy here, this y squared, you know, the first was I integrate was r squared. So the y will cancel, then y will come to r squared. If I integrate this y squared, because with respect to y, it's going to be y to the power of 3 over 3. Y to the power of 3 over 3. Then my upper limit is r, my lower limit is r minus h. So if I substitute for upper limit and lower limit, of course, you know what that means. It's going to be, let's assume I'm taking pi out of the equation. It's going to be pi for now. So for the first guy, it's going to be r squared. Don't forget upper limit and lower limit. Anyway, you see why. So r squared into brackets r minus, then y is there, right? So that's going to be r to the power of 3 over 3. What do I do? I close the bracket, minus, that's my upper limit. Don't forget, this pi is for everything. Then for my lower limit, it's going to be, open another bracket, r squared into brackets. Anyway, you see your y, put your r minus h, then minus r minus h to the power of 3 all over 3. Close the bracket and close the bracket. So if I spread pi over everything, it's going to be pi, and I open the bracket, pi to the power of 3 minus pi out to the power of 3 over 3 minus pi, don't forget pi is for everything, pi to the power of r to the power of 3, r to the power of 3, coming, oh sorry, there's no r here. It's just this to the power of 3 alone. Yeah. Okay, so if you use the expansion formula that we know, the expansion formula that you know from your basic mathematics knowledge. So from a basic, I'm going to come back to substitute. From a basic mathematical knowledge, you know that if you have alpha from your symmetric, alpha to the power of 3 plus or minus beta to the power of 3, you know that the expansion is going to be alpha plus beta, of an open bracket, alpha squared plus beta squared minus, sorry, plus beta squared. Okay, and if you want to tidy the equation, you can take it further from there by opening the brackets. So all we need is to use, you can use, if you don't want to go through this route, in case you don't want to stress yourself, you can just use your Pascal's triangle, 1, 1, 1, then 2, 1, 1, then 1, 3, 3, 1, because we're in the power of 3. Okay, so if I expand that, I'm going to have this on the board. So pi r squared h minus pi over 3 into bracket r to the power of 3 minus 3r cube h plus 3r h squared minus h to the power of 3. So this is it, 1, 3, 3, 1. So 1, 3, 3, 1. Okay. Let me cross-check this equation if it is tidied. We have pi r cube, then we have this, then we have this right hand side, r minus 3, r minus h to the power of 3. Okay. Okay. Now, the next thing to do is just to tidy up this equation. Oh, I didn't put it so that minus is going to be affecting everything. So I'm going to do like this. Okay, let me just clean this and come again so that I don't confuse you. Because of the space. I mean, okay. I'm trying to rub this last line off and take it again. Okay, so let's do that again. Of course, I've explained Pascal's triangle to you. I'll just apply it straightforward now. Okay, okay, so okay, now let me extend this equation. I was trying not to take off the left hand side. So if I have something like this now, it's going to be equals to pi r to the power of 3 minus pi r to the power of 3 over 3 minus, so I'm now here for the second bracket, open bracket to be pi, you know we have r minus h for the lower limit here, so it's going to be pi r squared. Oh, so I get where it is coming from now. I get where it is coming from. Just imagine that I've multiplied this pi at the front, I've multiplied to open this bracket. So there's going to be a pi inside of this bracket, and there's going to be a r squared here. So I omitted the r squared here. That's an error from me. So I mean, this place here, there's supposed to be r squared there. Okay. Now imagine that I've opened the bracket with the pi. So that'll be pi r squared. Then it is pi r cube, rather, pi r cube. Okay. Then minus pi r squared h, then minus pi over 3 into bracket r to the power of 3 minus 3r squared h plus 3r h squared minus h to the power of 3. Okay, so the 3 is for everything. Okay, so if I tidy up this equation now, if I tidy up this equation, I'm going to have, if I tidy up this equation, I'm going to have pi r h squared minus pi h to the power of 3 over 3, then will be equals to, of course, you know, if I open this bracket here, some of these guys will cancel out. So it's equals to pi h squared over 3 into bracket 3r minus h, which is what we are being told to prove. Okay, so that's quite easily done. Quite easily done. You just expand this bracket and you see that this we go with this, then this we go with, that's pi r, we go with this. So we're going to be left with this. Then if you tidy up this and this, okay? Are you following me? Okay. So that's that on that. So we have proved the volume displaced by the sphere. So the next thing we want to go to now is, what are the methods? All right, what are the methods? Okay, let me write something. Solutions of equations of one variable. Solutions of equation of one variable. Solutions of solutions of equations. Solutions of equations of one variable. Now, you are familiar with this somehow, but now we are trying to look for the approximate solution. It's partly the same thing you used to do under your polynomial equation, under your quadratic equation, where you have a standard formula such that when you equate f of s to 0, you can get an exact root. You know, you get, let's say it's quadratic equation, you can get s1 equals to a, You can get S2 equals to B, all right, such that your A and your B are the roots of the equation, okay? Now, that can be solved in that case. But now, in numerical analysis, when we're trying to do numerical analysis, we're not trying to use other methods to get the approximate solutions. And the point where we usually have solutions in our polynomial equation is the point where we equate to 0, okay? And that point where we equate to 0, if I have something like this, is the point where it crosses this x-axis. So if I have something like this. So at this point now, I know I'm going to have a solution. At this point, I know I'm going to have a solution, okay? That's where it is equals to 0. But if it does not cross this x-axis such that you have, let's say this is point A, up, point B, down. Okay, so you have opposite roots, all right? Solution will not exist. Okay, so what I'm trying to say is this. Let me explain. Let me explain with the methods so that I don't explain them in isolation. So let me begin with some of the problems or some of the methods we use in solving numerical analysis. So the first one is going to be bisection method. The first one is going to be bisection method. Bisection method. Bisection method. So what's bisection method and what does it entail? What is the principle behind the bisection method? Now, bisection method is actually a numerical method for solving the equation of the form f of x equals to 0. All right. The underlying principle that bisection method use is that which we call the intermediate value theorem, IVT. Bisection method uses the intermediate value theorem, intermediate value theorem, IVT. So how do we apply this theorem now, and how does it function? So what is the theorem? The theorem states that, I'm just going to say that, and I'm going to draw the necessary diagram. Okay, now bisection theorem states that if the function f is continuous in the interval a and b, the function f is continuous in the interval a and b, and k is any number lying between the function of a and the function of b. Don't worry, I'm going to give you the simple diagram. Then there is a point somewhere in a and b. There is a point somewhere in a and b such that the function of c is equals to k. What I'm trying to say is that, just say this is, let's say this is a graph, this y, this x, and we have curve like this. So what I'm trying to say is, let's say this is point A, this is point A, and this is A. Sorry about that, my pen. Oh, geez, sorry. Oh, sorry about that. I'm gonna have to cut the lecture soon, so take care of this. Then we'll continue in the next lecture video. I don't know what's wrong with my pen. I'm so sorry. Oh, so sorry. Okay. So let's say we have this. Let's say we have this. This is y, and this is x. And we have something like this. So let's say this is point A, and let's say this is point B. Now, of course, you know that x here is the independent, y is the dependent. So whatever s is, determine whatever y is going to be. So if I trace this point A, if I trace it to this point, let's say this is the point A. So that's going to be the function of A. Of course, in secondary school, you know that time where you say y equals to 2. When you want to draw a quadratic graph, 2x squared plus 1, then you now do a table. Now say x from 0, from 1 to 2, then you come here, you say 2x squared, then 2x squared plus 1, then y, whatever x is, determine whatever y is. That's what we're trying to do. So you have the knowledge of it already, just that we are solving it another way. So you see some. So since that's b, there's going to be a function of b. So we are saying that there is a point that lies between this point A and B, all right? That is, if this function is continuous, we are saying that there is a point K that lies between the function A and B. So this point here, point K, okay? Then if you trace the point K downward, that is, if you trace it to the curve, that's a point C. And that point K is also going to give us a function of C. All right, before I call this video, C is A plus B over 2. Always pay attention. For bisection method, the intermediate, that C, is the summation of A and B divided by 2. All right, so this is a function. This is a function of X. That's a function. Okay, now, having said this, when do we have a root? Or when do we, when do we have a solution? When do we have a solution? Because it is not all equations that are going to have a solution. Of course, remember there's something we used to call trivial solution when you're solving your mathematical equation. Trivial solution. So how do we know that we're going to have a solution in this bisection method or not? How do we know? So it's simple. You're going to have solution if you are having opposite signs. So let's say this is y. So if you go this way, let's say you come from down, upward, back. So this is point A. If you trace it here, that's going to be the function of A less than 0. That's what we mean by opposite sign. Now you can see that on this part here, this is S. It is on the lower part, which is negative part. Then your B is here. I trace it to that point. That's going to be the function of B. Is what? Greater than 0. And this curve is your equation. So because you are having negative part, or let's say opposite signs, that is negative here and positive here, then a solution will exist. That point where it crosses 0. Don't forget, we are solving the equation f of x equals to 0. If 0 is our major thing. At the point where x is 0. So there's going to be a solution here. Then you have opposite signs. Okay? All right. But if you have, you can have more than one solution, obviously. So you can have something like this that keeps going. So there's going to be solution, 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 okay? Or you can call it the root of the equation. But when the curve falls on just one side, that is, we have the curve on just one side, you can see that you are not having negative. There is no change of sign from negative to positive or positive to negative, all right? So solution does not exist in this case. Solution does not exist, all right? And there are also other points where you cannot confirm the existence of a solution. So in the next class, I'm going to be solving several examples. So subscribe, follow, like, and share. Thank you for joining me into this lecture. This lecture is brought to you from Topaz Engineering Tutorial. Please subscribe, share, comment, like. See you in the next lecture. Thank you.